Hello everyone, I'm Lee, and today I will present our work. This study addresses one of the key challenges in visual order: how to make agents trained in one domain generalize effectively to unseen domain. Visual reinforcement learning allowed agents to learn directly from pixels, eliminating the need for predefined state representations. This greatly broadened the applicability of order, especially in vision-rich domains like robotics and games. However, an agent trained in one domain suffers performance drop in new domains. The cause is the lack of diversity in the training data. Therefore, the central question is how can we provide agents to diverse domains during training? One intuitive solution is augmentation. Traditional augmentation like flips, shifts, or random convolution effectively increase diversity. However, they often harm the task-relevant information. More advanced approaches such as tree-based or normalization-based have been introduced to preserve semantics, but they still rely on predefined transformation, which limit diversity. To overcome this limitation, we turn to Stable Diffusion. Recently, several works have explored the potential of data augmentation using diffusion model. This generative model can produce highly diverse and realistic visual domains. Our insight is that in Stable Diffusion, the initial noise readily determines the generated domain. If we can control this noise, we can expose the agents to diverse domains. This forms the foundation of our approach. Here is the key principle of our method. If the agent episode return improved, we progressively shift the domain by perturbing the initial noise in proportion to that improvement. If the performance does not improve, we keep training in the previous domain to ensure stability. In this way, domain shifts are aligned with the agent's run in progress. Our framework, which we call DJ2, integrates two main components. First, the adaptive domain shift module dynamically regulates how much the domain can change based on episode return. Second, the sample generalization module incorporates saliency maps extracted from the battle network to preserve the semantics. We evaluated the effectiveness of our method on various environments and settings. For the encounter generalization benchmark, we compare our method against a wide range of baseline with different augmentation methods. Across our task, our method achieved the best overall performance. Further, we evaluated it on the protein benchmark. Here, the focus was to check whether our approach integrates well with on-policy algorithm. The result confirmed that our method consistently improved the performance across multiple games. This demonstrates that our method can effectively combine with on-policy algorithm. Another important observation is sample efficiency. Our method surpassed other methods by the 200,000 steps mark, showing our method can accelerate running. Finally, we conducted qualitative evaluations. First, we extracted the saliency map from the various images. Our method consistently concentrated on the task-relevant area compared to other methods. Finally, we visualized the augmented samples of our method. We observed that our method can generate a wide range of diverse domains while still preserving task-relevant features. To conclude, we proposed our DGA2. By adaptively regulating domain shift according to the agent's running progress through stable diffusion and preserving semantics with saliency maps, we achieve both stable training and improved generalization. We believe our method offers a promising step toward deploying other agents in complex real-world environments. Thank you.